All right, good afternoon, everyone. So today I have a bit of Excel type of a um, primer for you in some ways, and I have to admit I did get sidetracked by a colleague of mine, Dr. Mo, who likes to talk a lot, and so we got into a conversation today as I was meaning to be preparing this. So I spent a little less time preparing this with my own work and a little bit more relying on YouTube, which is also a great learning resource, right? So I'm going to show you a couple of videos here. I was hoping to kind of develop this, I guess, on my own and walk through it with you. But these two videos that I'll show you are actually pretty good for what I wanted to talk about. I also took a moment just now to look back on the homework assignment that relates to using Excel for perhaps a numerical solution, which is kind of something we're touching on today. And I think that it can kind of go either way. So I'll come back to that. I don't think you have to have what we're dealing with today to do the Excel sheet or to do that homework problem, so long as you recognize that it's, as long as you can get the analytical solution. We'll talk more about that in a minute. So what I have planned is to talk about a couple of different tools in Excel, kind of have some time to walk through them a bit with you to see what it might look like, and also to give you a recent example. I was working on a paper with my students, and we ran into a problem where we had to use the solver to come up with specific variables. We needed to fit a complex function and try to get a best guess for the variables in our case, to say that, okay, given this equation that we believe governs our system, the variables in this case must be this, that, and the other. So that's kind of where I'll go with that. Hopefully that will be interesting in the sense that we'll talk about kind of a research topic, disinfection and potential for bacteria to repair after UV dosing. So all in all, today we'll talk about what to do when we can't just flat out solve the problem, right? And you might be thinking to yourselves, well, I wish I knew that on every exam, because there's always a problem that I just can't solve. But specifically, problems that we're not even supposed to be able to solve with our typical analytical methods. Analytical meaning, like, we've talked about stuff like dc dt. If we're doing this integration and we know that we had minus k c, something like that, and we could integrate that, we remembered that the integral of dc over c from c naught to c, yada, yada, yada. There's that solution where it's the natural log, right? We have that analytical solution. So if that's not an option, maybe it's too complex or something, then what do we do? Well, Excel can do something for us. There's plenty of other tools. Certainly you could write a program in MATLAB, for example, or I think there's a website called Wolfram Alpha, which also has some pretty impressive capabilities for solving things. We'll definitely check that out at some time. Hadn't thought to mention that before, but this website can do some neat things mathematically too. I have barely used it, I just am aware of it. Okay, so one technique we could use is what we call iterative solving. And again, because I didn't spend enough time on this specific part of my lecture prep, I'm going to let somebody else and their lecture do so for you. So for those online, I'm probably going to have to take a moment to manage the audio so that you guys are hearing this through the system, but we're not getting the double feedback for the people online. So I'm going to end up muting myself. It'll just take me a moment to transition here. Make sure this volume's up a little bit. And just let me know if the volume is a problem online here. I think it'll be okay.
This screencast is on iterative solving using Excel. So a lot of times this is used to solve a circular calculation where we might have calculation involving one or many formulas. We have estimate for our x, and then we have an answer that's x, but then we keep going through this iteration, and for the solution to be correct, the estimate going in has to be equal to the output or the answer coming out of the calculation. So we're going to go through a simple example in Excel, and this is oftentimes used to solve things like when x is a function of x. So we have x equals 1 divided by sine of x. So we provide an estimate, and then we have an answer. So for our simple example, we have an estimate, which we start with, and that provides the answer. And then we'll keep on taking that answer and putting it back into the estimate, and hopefully if you set it up right, it'll converge to a nice value where we have x is equal to 1 over sine of x. So in Excel, we have our initial estimate for x, which is 0.5. Now the output to that is then going to be used as the input for the next iteration. So I'm just going to put a pointer here. The input for the next iteration is the output from the first. I can then copy this formula down, and if I fill down, let's say about 8 iterations, we see that the output 1 over sine x is approaching what you put into it. We can put in an estimate, answer, and keep going. And if we plotted that, you see that as we increase the iteration, we approach a constant x. So this is iterative solving. Another way to do this in Excel is called iterative.
Okay, so that was the kind of manual version of doing that. He's about to talk about using one of Excel's functions to kind of compress that into one specific task that Excel's going to do for you, making all of that and iterating kind of behind the scenes. So just wanted to do a small distinction here for you, explain that. Either way is fine. You could do it all out like that, and that would probably be my first attempt typically, is like do it stepwise like that. But if you want to be an Excel whiz, there's this other option, and I'll walk through and double check that we can find that in my Excel as well here in a moment. So I'm going to let him explain.
Iterative solving, and you can enable the iterative solver. So I'm going to put in just a guess for x, which will be our initial, and I'm going to have 1 divided by sine x, and I'm just going to put in a formula. The first thing we need to do, I'm just going to enable iterative solving. You go into File, Options, Formulas, and then over here on the right, Enable Iterative Calculation. For now, I'm just going to put in a 1 because I want to show you how you can do this stepwise, so I click OK. Now to do iterative solving, the output, which is 1 over sine x, is now going to be the input for the next x. So I'm just going to put a formula here, equals this, and if you don't have that iterative solver enabled, this won't work. It'll give you an error. So I press enter. Now the iterations I've set to 1, you'll see that the output now, this is the first iteration, it matches the output. If I go up here to File and if I change the maximum iterations to 100, I'm going to restart this to show you it actually automatically did it. But if I start with 0.5, I've got my formula down here. And now if I do equals this, and it converges on something that's very, very close to 1.114, which is very close to the solution. Whenever you have something x equals a function of x, you might want to think iterative solving.
All right. So that was the kind of first example I wanted to show you, and that was kind of that demonstration of that manual versus kind of that manual method. So iterating it out precisely. So if you had some graph and you weren't sure, what the true solution looks like, you could take it stepwise like that and say, okay, well, I'm just going to step from here to the next part on the x for the x value and find the y value. So really, it would be like, I don't know what happens between here and here, but I'm going to take that step and guess and get a little bit closer. doing it on this graph is probably not helpful. But if you encounter a problem like that, where you've got that cyclical thing, that iteration can be quite useful. So let's pull up Excel for a moment and just double check that we could do something like that. And I don't think the label here mattered. I think he entered this in as something else. He entered the formula into this field. So if we go into options, formulas, here's that iterative calculation. It looks like we can adjust that just like he said. Okay, so then I think he put in like that. And then you could check with that's our initial guess, I think. And then that's iterating just once if we do it that way. Or we could have it iterate 1,000 times. And then, depending on what our guess is, that's the way it's working, or a starting point there. So we can do something like that. I would go back and watch the video if you had a problem like this. Just a handy tool there. One thing that Excel can do for you. Sometimes you'll accidentally do that just when messing with Excel, and it'll be like, you have, something that depends on itself. There's an error here. Well, you can actually take that same phenomenon and use it on purpose to do an iterative calculation. So you just have to tell Excel that, hey, I actually do want this depending on this, and it to be back and forth. Actually, yeah, I think that's, yeah. So anyway, I might have got those formulas specifically there wrong, but you could go back to that video and figure that out specifically. Okay, so that's one thing I wanted to show. Next would be numerical solutions. So, and here's really getting at what might be most relevant for this class. Let's say I give you or if you encountered a non-steady state system, you got a really funky integral that you had to deal with, and you thought to yourself, well, I don't know how to solve that. And it's one of those things where I said you're not supposed to be able to solve it, right? There's no analytical method. If we got into second order derivatives or the second order rate constants, things like that, might get a little crazy. And so what could we do? Well, possibly use a numerical method where instead of using what we would call that analytical approach, where we end up solving that nice natural log of C over C naught equals minus KAT or something like that. Instead of doing that, we keep it in the dc/dt form like this, and instead of using the d as we do in calculus for that, with the calculus that infers all the limits and as it approaches infinity or 0 or whatever, and instead of having just dc here, what we see is if we take, again, this is a stepwise approach. We take c at some time that's n plus 1, so that's a fraction of a second further, minus what it is at the current moment. So that's that little change. That's what we're talking about when we say the change in c. That would be delta c, right? And so in calculus, we learned that it's nice when we can deal with this cleanly with assuming that delta is going to like an infinitely small amount. So in Excel, we could do that, except not make it assumption that it's infinitely small, just small enough to make a reasonable approximation, right? So that's kind of the goal with a numeric. And you see at the dt down here, the same thing's happening, where you have some small step that we're taking. We're not assuming that it's infinitely small and getting those clean analytical solutions, but we can do something that's a little bit more brute force, like, hey, we can cause this to happen in Excel. We can calculate for this value, and then change and step through it. So just a little glance at some calculations that are a little bit like that, maybe stepping the time interval 0.5 minutes each time or something like that. The Euler method is what's shown here. That's what this YouTube is going to talk about. It starts off deriving with the analytical approach. We've talked about this already. So I might skip around a little bit towards the beginning, and then I'll let them elaborate on kind of what I just said on how to put that into Excel and use Excel for that numerical type method.
This is an introductory exercise on...
Sorry, one moment. Let me mute this side.
Calculating a differential equation solution in Excel. We're going to take two different methods for calculating this. The first one is going to be an analytic solution to this equation, and the second one is going to be a numeric solution. So the analytic solution is by either separating and integrating. You can also use Laplace variables to do this. Let's just go ahead and review that. Okay, we have this differential equation right here. We're going to separate, so we're going to put all of the CA terms on one side and all of the time terms on the other side of this equation. So I have dCA divided by CA, and that's going to equal negative k, which is a constant, times dt. So we separate and then we integrate. So we're going to integrate from t1 to t2. Okay, just arbitrary time, and going from ca1 to ca2. Let me erase those. Okay, so we have our analytic solution by integrating this. Let's keep going. T1 step CA2 minus natural log of CA1. This right here is going to be natural log of CA2 divided by CA1, and that equals negative k times T2 minus T1. We're going to call this delta time. Right there, just the delta t. That's our time. Delta time, that c of minus k times t times ca naught. Okay, so here's my expression, my analytic solution by separating and integrating. Okay, let's do this numerically as well. So this kind of intimidates people for whatever reason. You have to take a class on it. You learn it in the class, but then sometimes you forget it very quickly, how to integrate analytically. Also, it's really only applicable for very simple systems, one, maybe two equations. If you get any higher than that, sometimes you got to do a lot more work to be able to solve this. So I also want to show you how to do a numeric integration in Excel that can help you solve the same equation, but you're going to be approximating it. You're going to use a numeric method instead of an analytic solution, but we'll compare the two. So we're going to solve it two different ways, analytically and then also with the Euler's method. So this is a general method that can be used for differential equations, where you basically just approximate the differential term with, let's say this is our initial concentration of 5, and then it's going to be decreasing as we go. We just take whatever point we're at, and we just take the last the slope right here. Okay, that helps us predict the next point. Then we take the slope, and that helps us predict the next point as well. Okay, and we do that with just a rise over run, you know, the CA n plus 1, that just means the next time step, and this would be the current. Okay, and that would be the next. And this down at the bottom is just our delta time. And then the thing on the right hand side is just going to be equal to negative k times CA. So this is our numeric method for solving it. It works out very nicely in Excel because we can do one formula and then just drag it down. So let's open up Excel and we'll see if we can solve this equation both analytically and numerically. Okay, I'm going to put in a couple constants here. I have my C A naught, and I'll make this a little bigger. Okay, there's my CA naught, and I'll put 5 there for CA naught. My delta time. Okay, I'll just put that as delta. If I change this to symbol on the font, it'll make a nice delta there. Okay, and then I have 0.5. That's going to be seconds, and this is kilomoles per meter cubed. Okay, my K value is going to be 1, and that is an inverse second. So let's create our table here. We have time, T, and I'm just going to have, just go ahead and express this as this plus my delta T, just so I can change that in one place, and then it's going to go ahead and just change it for all of them. So if I just drag this one down, I'm going to get my time points, and I'll go down to you know, about 7. First of all, do 7. Okay, great. And then for my CA, and I'll do this one as my analytic solution. Now if you remember, that one was just equal to my initial concentration. Let me pull up that just so we can see that one again. Okay, there it is, and do my initial concentration times the exponent, okay, of negative k. Don't forget the F4, just give yourself the dollar signs, make it fixed, times the time, and there. And what I'm going to do now is just go ahead and double click this, and it'll drag this formula down.
Okay, so what he just did is just filling in Excel with the analytic solution. So that's not super crazy. Basically, he's just using e to the minus kt, solving that in this part. So the next part is where he's bringing in the Euler method, where you're estimating a slope between the current step and the next step. And then he's also going to show control over the step size itself, which I thought was kind of a neat way to go about it, controlling that delta t from over here rather than manually changing it over here, which is probably what I would have started doing. So I think that's this part is just kind of using the analytic solution that he already knows. So the next point then is a little more interesting.
And you can check it at different points if you want, just to see if it got the right values in there. Okay, so there's my analytic solution. Let's go ahead and do a numeric one as well. Okay, so numeric, we're going to start with a value of 5. Okay, I'm just going to put equals this value right here. That's just going to be our initial condition. And then, let's see, let's go back over here. Okay, so we're going to use this formula right here to help us calculate the numeric. This is called Euler's method, explicit Euler's method. So that's just going to be equal to, if I solve for CAN plus 1, that's my next time step, it's going to be equal to whatever on the right hand side of that expression. So that was equal to negative, I'll put some parentheses here, negative k times the prior CA value. Okay, don't put any dollar signs there because we want it to drag down. Times my delta t. Put a dollar signs there to fix that value, and then plus, and then we're going to add the prior value again. Okay, so now I'm going to fill this one down, and then we're going to see how changing the delta t gives us different answers. Okay, makes it more or less accurate. So let's go ahead and just select this region right here, and we'll go ahead and insert a scatter plot. Okay, so there's the numeric versus the analytic solution. You can see that the analytic solution is going to be accurate to machine precision. The numeric one is going to, the solution is going to change depending on what we have for our delta t. Okay, so if we make that smaller and smaller, okay, I'm going to make this 0.5. Okay, so they're going to match up much better if I make that time step smaller. Okay, I'm going to fill this down just a little bit more, and let's do this. I'll move this plot out of the way. Let's fill it down to more time steps. Okay, I'm just going to drag all three of these down, give us some more. Okay, we'll go out to 1.9, and then I'll go ahead and just let me just go delete that plot. I can also drag, I could have just dragged that data range down as well, or it's very easy just to insert a new plot as well. Okay, so there's our the analytic versus numeric. You can calculate the difference between those two, and that would be an error of integration using the numeric method. Okay, let's change this to I'm going to come back up here, paste my plot in. Let's change this delta t and see what it does when I give it more and more values here, 0.5 or larger values. You can see there's going to be an error of integration. I'll go ahead and change the just so it doesn't scale too much here. Just go ahead and set the maximum of my x to 5, just so I'm always looking kind of at the same region as I change this delta x. And if I go to 1.0, 2, then it's going to kind of go unstable. Okay, so as you go further out, it's going to become less and less stable. Let's see if we answered all the questions here.
Okay, so you guys seen that stuff before? You've done that stuff before? No? You done it in any other program or had anything like it? Okay, so that glad I brought that up then. So it's something that certainly can be a very strong tool. There's a lot you can do with that type of thing. In this case, we were looking at essentially estimating the solution to a differential equation. I'm going to show another case in a minute where we presumably have a solved equation, but we're trying to find what the parameters are. And there's like 4 different parameters in the thing. And so we're going to use another function from Excel called solver. It's kind of like solve for x, except this time it's like, well, solve for the best fit if there's x, y, z, and a, right? It's like there's several things going on. Play with, and Excel basically iterates attempts at minimizing that least squares regression or whatever for a function. Okay. Okay, so I want to tell you a little bit about some research I've been involved with recently of just a couple slides on UV disinfection, which is, to me, a pretty interesting topic, to set the background to see the data that we had to use a solver for, okay? So one of the things that we've been working on with research in my lab is, well, we know UV works as a disinfectant. We know that it especially works in what we call the UVC range. That's light that has a wavelength. So if you look at the wavelength of light, the distance between two waves, that's called the wavelength, or two peaks, let's say. That's going to be our lambda, and that's going to be nanometers. So in the visible range, we don't get much germicidal effect. If you have hot sunlight, hot conditions and bright sunlight, that will promote some destruction of bacteria, but it's slow, it's not very reliable. And really what mostly is happening with sunlight, if you're putting water out in the sun, is that mostly action by the UVA and some photochemical reactions that will happen based on stuff that's inside the cells or stuff that's around them. And it's just kind of a slow process. But if you use UVC directly, a shorter wavelength, it's kind of higher energy, then you can actually denature DNA itself. Fortunately for us, almost all of this is absorbed by, well, practically all of the UVC is absorbed by the ozone and oxygen layers in our atmosphere. So by the time the sun's UV rays, including X-rays and all that the sun is emitting, by the time it gets to us, we're really only getting pretty much the visible and what we would call the UVA range, and a little bit in the UVB. By the time it's down to that germicidal range, it's pretty much all absorbed. Now, if we look at the wavelengths in terms of what lamps we have that can emit UV and look at how effective those are against germs, this germicidal effectiveness, anything in this region of this gray outline here, anything that emits light in that region can have some impact. And so sunlight, we get a little bit right in here, and that's about it. The sunlight goes more up this way, but we see that that's not going to have any impact on the germs there. At least not a direct impact, like I said. So typically what we've done is used mercury lamps. We've got mercury lamps, fluorescent lamps in this room even. The deal is those are coated with phosphors that absorb that harmful UV, and then this coating gets excited and emits white light. So it's like we create this UV light and then transform it with this coating, absorb it all, and transform it into white light. And so the fact that there's plastic and plenty of air between us, even if a little bit of the UV did get through those somehow, we're not getting hit by it here. So rest assured on that regard. But the low pressure mercury lamps emit strongly right here, that UV 254 wavelength. If you get a different type called medium pressure, you still get some over there, and it's a little bit more spikier, a little bit more polychromatic, we could say. Certainly effective. Sometimes it's used based on operating conditions. Sometimes it makes sense. Now, what we find interesting is the fact that we now have LEDs that can emit into the UV, and those are emitting, we have a little more choice in the matter. So we have some in my lab that are emitting something like this. Some are made that emit kind of with a peak like that, and we can basically select different colors of UV light. The question there that we were trying to answer is, well, does that impact the mechanisms that bacteria have to repair themselves from this type of damage? Because a lot of bacteria have some mechanism to repair DNA damage from ultraviolet light, because a lot of bacteria would prefer to be able to survive a little bit of damage if they were, out in a lake or whatever. So the way that the UV damages it in the first place is important, and that is a mechanism we would call dimerization. So if we have a DNA molecule and there's certain groups here, this thymine and thymine group, where there are two of those next to each other and those molecules absorb some of this UV light, they can dimerize, meaning they react with each other and form kind of a linked molecule. Does like a combo of two molecules there. And that linkage acts like if you took some super glue and put it on one side of a zipper, right? Then whenever you're trying to open or close that zipper, which is what DNA does to replicate, then the zipping mechanism is going to get stuck, and it's not going to be able to pass that point. And so some bacteria have an enzyme called photolase or whatever, and that enzyme can repair those specific types of spots. So that enzyme was discovered, somebody won a Nobel Prize for it. Turns out there aren't very many of those molecules in a given bacteria cell. They were trying to harvest that, whatever enzyme was doing that. They're like, hey, if we can get that, this will be a great like skincare treatment for skin damage from sunlight, right? You can repair sunburn pretty quickly, or at least any potential DNA damage. But turns out there's like somewhere between 1 and 5 of these molecules in a bacteria cell. They're just going around doing this all the time, and they're activated by light themselves. And so this and future research discovered that light in kind of the blue, slightly UV range maybe, can activate this enzyme, repairs damage done by stronger UV. So presumably if a bacteria is out in let's say, in nature, exposed to sunlight, it's receiving damage and also repairing that damage continuously. That's kind of the theory there. So what happens when we want to disinfect our water and keep it that way, we have to consider the fact that, let's say we have a log plot here. I'm going to say some concentration of bacteria. Let's say that's colony forming units per liter, something like that. And then what I'll do is instead of doing like log of that, I'm going to just say this is a log plot by kind of writing it out like that, 10 to the 6, 10 to the 5. So my scale is log here. Hopefully that'll make some sense. So if we look at what happens over time, and we'll say minutes or something, if we do a UVC exposure, so this germicidal stuff, we'll kill them off pretty quickly. So let's say we start with 1 million bacteria per liter, and then we expose it to UVC. Well, typically it only takes a few minutes, and on a log plot, it's going to be a first-order disinfection, a first-order rate. It's going to disinfect. It's going to happen quite quickly. So we're going to have a relatively straight line there for the disinfection part. After that, there's some question about can they repair themselves? And so we'll say that little section here, that's UVC dosing. After that, we could consider a couple different scenarios where they may be allowed to just sit in the dark. There are some repair mechanisms they have to, like, some of the bacteria will be able to recover and survive, even though we killed, if we look at this, this would be 90%, 99, 99.9, something like 99.99% of the bacteria here from what I drew. So if we put them in dark, it turns out, especially if they have, and this is not, the first few things would be minutes, like a few minutes, and then we'll get to hours, pretty much. So that's the way I'll draw this. If we leave them in the dark, then they can regrow a little bit, something like that. Then if we give them some bright sunlight, they can actually repair from that photo repair process rather quickly. And they'll repair pretty significantly. Maybe we thought we had 4 log reduction, that 99.99%, but really, after an hour in the sun, we only have now an effective 99% reduction. So that kind of changes the situation if we're disinfecting wastewater especially, or even if we have drinking water and we ran out of residual chlorine and it's sitting on the counter and in the sun, if that was the case and there's bacteria that could be repaired still, maybe we have some repair. Says a lot about bottled water. They've intentionally taking out all the chlorine, any residual. Makes you think a little bit there. Anyway, so then one thing that'll happen though is the sunlight will eventually start killing them back off again. They're already a little bit weak. And so the curve ends up looking something like that. So we have an initial rate at which they're killed. This would be our UVC. What I'll say is maybe a K UVC, so some rate where that happens. Then we have some repair here, so I'll say some rate at which they're repairing. And then the sunlight is actually harming them still, so eventually they're decaying again, so then we would say K, I don't know, sunlight or something. Okay, so this becomes an awkward function. And what we did was we followed a paper. I'll pull this up for a moment for you. And essentially, this paper was dealing with exactly that problem. And we'll see some graphs that kind of look like that and their equation. So they showed essentially some previous studies had done the same type of analysis. This can the bacteria repair themselves? Turns out yes, but a lot of studies didn't use strong sunlight. They just used like some indoor lighting, and the bacteria could use that to repair, but then it wasn't harmful to them. So this paper was like, hey, well, the sunlight's also then hurting them, and we need to account for that. So that was kind of an update. And that's what we followed. We'll come back to that. And it turns out that the way they decided to analyze it was a survival fraction. This would be something like n over n naught, was their basis that they wanted to take a look at. So when they solved this, they wanted a function for that. So really what they're looking for is kind of a dn dt type of equation. And you could start at like a n for the disinfection here at this point. So anyway, the stuff gets a little bit complex, but if you take a look, if you want to find that survival ratio and you've got all this stuff happening, well, it turns out you're going to need the initial disinfection, and I think they just assumed there was some already, but then after that you have the repair, so some rate of repair, but that only takes effect on the percent that did not survive initially. So you can't repair a perfectly happy cell, right? The perfectly happy cells that are still living here that tend to the second amount of them, you're not going to be able to repair those. So you have to multiply this by like a fraction that was hurt, fraction damaged. And then you've got some, so that's going to be the repair, but then you've got the amount that is being hurt again, and so then you're going to have minus some rate of sunlight damage times, and that'll be dealing with the fraction that's still viable, right? So just kind of painting some context here of like what's going on, how are we mathematically approaching this, to show you why Excel was needed and how that helped us. So they went on to derive an equation based on that. And I can show you what they did here. Sorry. So ultimately, they derived this equation where they had the survival at some time t is equal to some parameter Sm times e to the minus some rate constant times time, minus some parameter minus the initial survival, so survival at time m, I guess, minus the survival initially times e to the minus, and then a couple rate constants together times time. So that was their solution to the kind of this that I just generally wrote out in a general form. The question then became, what are these parameters that were in there? So the SM, so we'll say here's one, SM, which is the maximum survival minus the initial. So this was the maximum survival after repair, I believe it was. So this is one parameter together. We had just SM by itself was a parameter. And the reason I say SM minus S naught was a parameter, that's one of those things that's describing how much are still surviving or how much were damaged, right? It's one of those comparisons there that we're getting in the math here. So we've got that one. We've got SM by itself, like the maximum survival. That's probably the point at which they regrew the most. So what value was that? There's this KT. I think that was the decay. No, I think that was the repair K. And then there was this destruction K for the sunlight as MS. So 4 different parameters in here, and not a great way to know for sure any of them. So what they wanted to do was build a model based on their observations. If they performed these regrowth experiments, checking how many are regrowing at different times for a lot of different cases, does this depend on how much UV dose they got in the first place? Does it depend on the type of bacteria? Does it depend on if it was just generic wastewater bacteria? So that was their paper. And ultimately, they collected all this data for different cases, and ultimately they came up with a way to estimate these different parameters. So the SM, they got data and they built a relationship, some curve fit for that data. They did the same for this K and the SM minus S naught, and for the MS, which did not really have a relationship. And then they compiled all of that, and they said, okay, well, here's pretty much the average MS values. We'll use those averages. That one didn't have that relationship. These other ones, they had a nice fit where they could see some relationship with the UV dose compared to that parameter. And so they made empirical relationships, like SM minus M naught, S naught, for this particular type of bacteria is going to be 5 times e to the minus 3 times the UV dose. So some relationship to the UV dose there. So all of this to say, they got all these different equations from their data, and the way they were doing this was by fitting each component here. And so when we wanted to replicate this for the LEDs to see if they were different, what we did was we took our own data, which is the blue and the green dots. The blue here is the UVs, the fluorescent ones. Basically should be the same as what they did. And the green would be the LEDs, kind of the new technology. And we thought, because we had the same exact bacteria, we had UVC just like them with the mercury lamp, we thought we should be able to repeat what they did. In terms of the amount of UV dose, we were very careful how to calculate that. Well, it turns out if we put our parameters into their model, it was way off. So our parameters put into their model gave us this dotted line here that goes like that. So when we used their equations here to solve, it just was not anywhere near the blue dots that they should have been. So we were hoping that their model would fit our blue dots like so. That would have meant that their model works for us, and that was all well and good. Well, turns out I don't think they calculated their UV dose as simply as we did. We used a very simple batch case and we knew very carefully the UV dosing, and all of the bacteria are pretty much getting the same dose in this little tiny reactor, batch, perfectly mixed, very close to an ideal reactor. Their case, they're using this pilot plant and changing the UV dose based on how fast they're putting water through it, I think. And so with this pilot plant, not all of the bacteria will receive the same dose, and the dose calculations are complex. They didn't even describe very well what they did, so there's some difference there, I think, that's the matter. But given that, we still think their equation is right. Their net equation for this growth and then the repair, so that repair part and the destruction from sunlight sort of stuff. So we wanted to use their model, this equation, and then use a fit to get our own parameters, to essentially to draw these dashed lines. So these dashed lines here are not. That's not just Excel connecting dots. That's actually a regression or a line drawn based on that regression that we made. And you can see that because it's not fitting precisely each dot. Okay, so here's just to show you when we took their parameters and put in our situation, we got these parameters. After that, we took it into Excel, which I'm about to show you, and told Excel to do the solving to fit and guess for each of these parameters what gives us that best fit, and then we can compare and say, okay, well, our fitted values here were much different than what that paper thought we should have there. So that in itself was a pretty interesting result from the paper. Okay, and that's just kind of the same thing. And before I dive into Excel, really what we're after here is how do we know truly the effective bacterial load that we might be discharging to wastewater? The importance there of defining our initial conditions. We kind of did it differently at first and had to adjust. And that calculating that UV dosing was really kind of the takeaway for that paper, that difference there. Okay, so what I wanted to show you then is a bunch of mumbo jumbo on Excel. I'm going to try to make this clear. So in Excel, I'll do a big picture first, right? Bunch of stuff in Excel. This is where that data was coming from. These large columns here, that's where we're doing some iteration across time to see, okay, if we give it like a full several hours of time with some sort of fit, what's that going to look like? So that's how we got our lines here. We only have a few data points because it takes a lot of effort to do these experiments and get that data, count all the bacteria. So we only have a few data points, and so then that whole bunch of data points, that's our Excel calculation to say, okay, given these parameters, this would be the readout of our prediction. So that's all our prediction here. Our data itself was just, let's say, this. So just a few data points there at, up to several hours there. And we had UV 254 that we were trying to fit. So that's the mercury lamp versus our LED, which is the 278. Now, for each of these, we ended up calculating a modeled, taking that model, the mathematical model, this one, and we told Excel, okay, use that to minimize the variation. So when I say variation, I'm saying the variation between this dot and the line that it draws. Okay, this is actually how linear regressions work, is it's finding the function that minimizes all of that. So for a linear regression, if we have a dot here, dot here, dot here. Excel is going to find the line that minimizes the distance between all of these guys. That's how it works. So we're doing the same exact thing. Excel's going to do that same exact thing for a curvy function, given that we have this function entered into Excel, and it's going to follow essentially those directions. So using that instead of y equals mx plus b, and using sm and ms and sm minus s naught and all that instead of x and y. Or maybe if we didn't know m, it would, so m and b, I guess, would be the better way to say that. Instead of using m and b, it's using those 4 parameters. Okay, so let me see if I can dig through here. Okay, let's see. All right, so this predicted ST, that's where I entered, given some time, t, so we see that the 0 is highlighted, it's calling for the time 0 there. Given that, and given these 4 parameters, the SM, the MS, the KS, and the SM minus S naught, as 4 parameters there, we have a calculation here, so we can hit enter there. Then what we did was we used solver, and it might take me a moment to remember because it has been a little while. You go to data, and there's a data analysis package. It's kind of, you have to add it, make sure that it's enabled. All Excel should have it, but you have to, I think, go into the add-ons or add-ins. Yeah, Excel add-ins, you hit go. And this analysis tool pack, you have to check that. Oh, excuse me, not the analysis, the solver tool, solver add-in. You have to check the solver add-in, hit OK. If you ever do need to use something like this, you'll find tons of tutorials online, I'm sure. Just kind of wanted to show you this, what we did. So then, with that solver, let's bring that up. What we want to do is set some objective, like I want this cell to be calculated, and it needs to be, we're going to set this cell here to be minimized. We want to minimize the cell that we say this is the error or the variation for these values. So we're going to minimize the variation, and to be honest, I did this a little over a year ago, and if I stumble through it right now, I'm just going to make a mess, and it's not going to be clear. So what I'll just summarize and say is we have this SSE here. This is the, I think this is the sum of the standard errors, and then we can calculate what's called the total variance. It's basically just that the total amount that the points are varying away from the curve that we fit, and that's our target to minimize. So we minimize that error that we can calculate, and these error values are coming from these variations, which are coming from, again, this is a little bit iterative here, this is coming from these equations or these calculations, which are coming from this model. So Excel is going to iteratively change the model parameters here. That will give us a new ST. That's going to change the variation. And then we're going to check that variation against, our system here. And actually, I'm sorry, I just totally messed that up. Almost had it right. Let me clarify. The ST here, this is our actual observations. So what we're checking here is the difference between our predicted observations here and the ones we calculated by doing lab experiments here. Okay. At any rate, I'll try to get a cleaner, simpler example that you guys can try on your own and we can work together later after the exam. Wanted to give you this time to show you some of these tools. I don't feel like I did this one justice, so we'll come back to it, but it is pretty neat because you can then get what we got here. With the new parameters, we went back and put those parameters into like that full 540 minutes and drew out one of these curves, right? So this is this data here. And we then can see how that maps to our data, and it maps decently well. So it is very useful. It is something that is you might find use for at some point. So any questions or comments, or would you like what would you guys like in terms of hearing more about Excel? Any thoughts?
I like hearing about it because I never learned about Excel in my other classes.
Yeah, if I'm being honest, I kind of have no idea what they're doing. I'm following like what you all are doing, but I wouldn't, if you had asked me to do this before, I wouldn't have any clue, so it helps.
Okay, so maybe some problems, assignments to challenge you to do some things. Not this level, because that was crazy. And
yeah, I was going to say, I mean, this, I might as well just shut my computer off.
Well, you could get there, and in fact, some encouragement for you. It's not like I've used Excel for my research every month of the year since I've started doing research. But I came back to this, and I was like, I know there's a way to do this. I know it's called Solver. Let me go YouTube this and figure this out. Play with a simple case. Make sure I can do that with a very simple equation. And then within a few days, I was able to get this stuff going. And then I was like, hey, grad student, look what I did. This is fun, and I think this is helpful. And so the two of us then just kind of took a look at it and kind of sorted through what we wanted to do. So you should see that my original spreadsheet is much more of a mess than this one. Bad ideas everywhere and stuff. So anyway, it's possible. And once you kind of get a feel for it, and I'll try to give you some reasonable use for it, we'll take a look at that.
I mean, I don't want to hold on this one Excel then.
So in the homework here, I was exactly taking a look at that. And this is essentially one of the book problems. I just kind of changed it up a little bit. It says, use an Excel spreadsheet or equivalent to determine concentrations if the process is producing that produces sewage shuts down. Basically, it stops being steady state, right? You get a non-steady state system. What do you do? And it's saying calculate points at 1-day intervals for 10 days. So I don't know for sure, because I haven't tried solving it yet myself. I don't know if we can use an analytical approach, like our C over C naught equals e to the minus kt type of thing, something that we can analytically do from the derivation. I think we probably can, and so I think it's probably just saying plot 10 data points. So, and watch that over the 10 intervals. Maybe it's not really going to be a convenient way to iterate, so they're asking us to take the function that we get that we don't know how to solve. Maybe it's an integral that is just messy, but take that and break it into just tiny steps of time and change in concentration, right? Because we could calculate that, and then we're just doing that over 1-day intervals, which seems like a lot to me, like a long interval, but you could do that Euler method that we saw.
Okay. I have a question with the exam. So it's next week, right?
Yeah, so the exam is a week from today.
Okay. What's it gonna be like? Like, what are the questions gonna be like on that?
So it's my goal with the exam, because the question, by the way, is what's the exam going to be like, is to give you some word problems that are not so involved that they're going to be take a painful amount of time to do all the unit conversions and all of this and that, but to show me that you're capable of it, and to show me that you're capable of using a mass balance or understanding the principles behind a mass balance. So
Is it going to be like the homework questions or easier than those or what?
So my thinking is that first set of homework questions were probably on the easier side. These ones are a little bit longer. It's a question online as well. How many questions will it have? My goal is to give you, and again, I haven't taught this specific class before, so I will have some calibration. If I accidentally make it too hard, I'm going to calibrate with my grading. My standard approach to exams is to make them a little bit on the challenging side and then give partial credit when I see you are understanding the process. If you get a wrong answer but you have all the process correct, you'll get most of the credit, right? So that's kind of my take on it. I want to measure your learning with it, and I find that's easiest to really sort everybody by how much you've learned by putting it a little bit challenging but not too much. Because if I make it too challenging, then I need to like drop a question or something, and that's just a mess. I don't want to do that. I don't like to do that. So I don't want to err too far in that sense. So I imagine it'll probably be between 4 and 6 questions, and they might have a subpart or two. Like, you know, some, like if it's 4 questions, maybe they'll have 3 subparts or something. But I don't want to so that you're spending half the exam on one question, right?
So, like, when you said you wanted it a little challenging, so like the homework then, or?
Well, to be honest, I haven't solved either homework yet, and so I don't know exactly how involved these are. I looked at them, I thought about them as I went through, but I haven't gone through them yet, right? So I have a difficult time relating them exactly to the homework.
Yeah, that makes sense. All right, I was just wondering. Thank you.
But I imagine if it was a homework that, you know, if you already completely understood the concept, then it took you like half an hour. That was probably similar, except the homeworks are going to have more unit conversions and things. I'll probably have a few that are specifically asking for unit conversions or checking that. Normally what I would do is focus on, let's say, the mass balance approach. This class we're really doing both, so there will be some easy or straightforward questions that are, hey, here's a lot of units, make sure you're tracking them and, you know, accounting for things correctly, practicing that and showing me that. Question here, will there be a practice test posted? No, again, since this is my first time teaching the course, I have no materials for it. And so I unfortunately don't have that. I would encourage you to go through the book questions. If you take a look at chapter 4, we covered almost everything except the energy balances, which we'll do later. So anything energy related, don't bother, but otherwise the stuff in chapter 4, some of the stuff in the air chapter, which I think is 12, the simple side of it could be good because we did cover units beyond just kind of the simple stuff. We'll have more time for this. Happy to continue answering questions, but we will have more time for this probably on Tuesday when we go over the homeworks. My plan will be to go over them quickly, especially with the units ones. That first homework is mostly unit conversions, I think. So I don't expect you to have a ton of like, how did that work kind of questions. So I don't want to spend too much time. I'll try to spend more time on the homework too and give you time to chat about the exam then as well. But any other questions? Okay. All right, so let me, and one thing I'll say also, we'll do a quick Kahoot. I'm behind on collecting all the Kahoot data. It's all there. I will go back and get it. I just need to do that and assemble your current grades and all of that gradebook setup. So I'll probably be doing that and trying to get your assignments graded before long. I know there's going to be midterm grades coming up that I'll need to meet as well. So all right, we'll just do this. All right, so let me know if you're here. If there's any other questions, happy to take them while you do this. 17 here and 12 online, so hopefully we'll get about 29. Maybe we have 17 here and 6 people paying attention online. Okay, we'll give it another moment. All right. Okay, so we'll have the exam review, go through the homework solutions, and again on Tuesday, make sure you scan your homework before you turn it in, just to have that reference to study from. I will post the solutions to both homeworks as kind of PowerPoint with the solutions written on them. Even if I don't have time to go through them all the way, I'll finish writing them out, and you'll have the solutions to study from on Tuesday. So, all right, with that, have a good weekend.